So, hello everybody. My name is Nguyen. I'm a postdoc fellow at Basque Center for Applied Mathematics in Spain. Today, I would like to talk about regular projections in our minimal structure. So, the contents of my talks, including regular projection, regular covers, and the proof of the main theorem. Let me start with the motivation of the problem. The regular projection theorems were introduced by Mostowski and was extended to subanalytic categories by Barusinski, and it was used in the proof of existence of Lipschitz stratification. And recently, Barusinski uses the key to prove a results called regular cover theorem for sub-analytic set. So in the same paper, Barusinski asked if the regular projection theorem and regular cover theorem holds in minimal structure. The reason asking this question is because the classical argument of Mostowski and Barusinski as well, they use a results called Baruski-Buser theorem with parameter, and that result doesn't apply to minimal structure in general. So in this talk, we going to deal with the question of Barusinski. Namely, I'm going to give a Lipschitz version of regular projection for definable set in minimal structure. Actually, it is not the original one, but it's strong enough to make sure that the regular cover theorem holds in any minimal structure. So let me continue with the definition of regular projection. So let lambda 0 be a vector in Rn minus 1, and we denote by lambda 0 from Rn to Rn minus 1, the projection parallel to the vector sigma lambda 0 equal lambda 0, 1 in Rn. So given P, so let X be a subset of Rn, epsilon C bigger than 0. The projection by lambda 0 is set to be epsilon Cp regular at the point x0 in Rn with respect to X if the following condition satisfied. The first condition is the restriction of the projection to X have to be finite. And we look at the cone starting at x0 with the radius epsilon along sigma lambda 0. So the second condition is that the intersection between X and this cone is either empty or disjoint union of CP manifold. In the picture, we can see that the intersection is the disjoint union of two CP manifold, gamma 1 and gamma 2, and gamma I can be written as this form. And beta I here is CP nowhere vanishing function. And the third condition is kind of a Lipschitz condition. That is, the gradient of beta I is bounded by C times to the modulus of beta I. So what is the geometric meaning of the condition 3? It means we can shrink the cone a little bit such that the intersection between the cone and X can be considered as the union of disjoint graph of Lipschitz function. So given P, so we call a set in Rn minus 1 a set of P regular projection for X if there exists epsilon and C bigger than 0, so that every X in Rn there's a vector in lambda, so that by lambda here is epsilon C P regular as X with respect to X, of course. So Barusinski proved that if X is compact subanalytic set in Rn, n dimension of X is smaller than n, then X has finite set of analytic regular projection. And he used this result to prove the regular cover theorem. So given U in Rn to be open definable set, so definable regular covers for U is finite families of open definable set Ui, such that U is the union of Ui's, and each Ui is definably homeomorphic to an open n-dimensional ball in Rn, and there's it C bigger than 0, so that for any X belong to U, the distance from X to the complement of U in Rn is bounded by C times maximal of the distance from X to the complement of Ui in Rn. So Barusinski proved that if U is open bounded subanalytic subset of Rn, then there is a subanalytic regular covers for U. So to deal with the definable set in our minimal structure, we introduce a new condition. We call that 3 prime. So let m bigger than 0, the condition 3 prime means for any X in the intersection between the cone and X, and for any lambda in near lambda 0. It's been in the ball center as lambda 0 with radius epsilon. So with that data, so the angle between sigma lambda and the tangent space to X at X is bounded away from 0. So if we look at the picture before, so the condition 3 prime means we take any line through X0 contained in the cone, and we take any X in the intersection between X and the cone and look at the tangent space at X of X. And the condition 3 prime means the angle between the line and the tangent space is bounded away from 0. So it's easy to prove that the condition 3 prime implies the condition 3. So we prove further that a given X to be a definable set in Rn with the dimension smaller than n. It means the interior of X is empty. And then there exists the definable bi-elliptic homeomorphism from Rn to Rn, epsilon bigger than 0, m bigger than 0, and a finite set lambda in Rn minus 1, such that every X in Rn there exists small lambda in lambda, such that by lambda satisfies the condition 1, 2, and 3 prime with respect to the image of X under the map H. Because the condition 3 prime implies the condition 3, so we have the following result, that if X is definable subset of Rn and the dimension of X is smaller than n, and given P to be integer number, then there's a definable bi-elliptic homeomorphism so that the image has a finite set of bit regular projection. And by using this theorem, the main theorem, and the argument as Baroshinsky, we can prove that every open definable subset of Rn allows a definable regular covers. So let me make some comparison between our results and the results of Baroshinsky. So if you look at here in the results Baroshinsky, he has some kind of boundedness. Here's compactness. And in the regular cover theorem, he also needs the boundedness. And in our situation, we don't need any boundedness for the given set. This is kind of understandable because of the finiteness of our minimality. So let me move to the idea of the proof. So first we going to construct or going to find a set delta in order 2n such that the dimension of the fiber of delta at x for every x in Rn smaller than n minus 1. This means the set delta is not very big. So we consider delta as a Basque set in this case. So, and the delta satisfies the condition that if the cone at x0 with radius epsilon intersect the fiber of delta at x0 is empty, then the condition 2 is satisfied. And next, we will show that Rn can be partitioned into finally many definable set, sigma I. And for each sigma I here, we can find lambda I and epsilon I, so that the intersection between the cone center at x for every x in sigma I, and with the radius epsilon I with the fiber of the Basque set at x is empty. This means the condition 2 is satisfied. To deal with the condition 3 or condition 3 prime, we use result Nguyen-Valette. Nguyen-Valette proved that after a definable bileptic homeomorphism, the set of good direction in the sense of the condition 3 prime. It means the angle between the direction and the tangent space is bounded away from 0. He proved that this set is not small. It means it has dimension n minus 1. We show that the direction lambda I here could be chosen to be inside the set of good direction. And then the condition 3 prime satisfied. And for the condition 1, so this is more easier by the fact that the set of direction such that the projection along this direction is finite is a definable then set in Rn minus 1. So that allows us to make the set of good direction a little bit smaller in such a way that all the good direction we are choosing satisfy that the projection along them is a finite map. So let me move a little bit more detail about the proof. So first of all, I want to recall the result of Guillaume Vallet. So he proved that given A to be definable subset of Rn of dimension smaller than n, then there is a definable bi-elliptic homeomorphism H from Rn to Rn such that the image of A over H has a good direction. So what good direction mean? A good direction mean is a vector in order n so that the angle between this vector and the tangent space at every regular point of the given set is bounded away from zero. So I would like to remark that not every given set has a good direction. For example, a circle doesn't have a good direction. But after a bi-elliptic homeomorphism, its image has at least one. So we need also the following results. So here we define a box in RK. So we have a result like let C be a definable subset in Rn, and let B to be a box in Rk, and let delta here be a definable subset in C cross P, so that the dimension of the fiber of delta at every x in C is smaller than k minus 1. Then there exists a definable partition of C so that each element of the partition, there's the box in B so that this intersection is empty. And now we back to the given set in the main theorem. It means X here is a definable set in Rn and dimension of X smaller than n. So we define the set of regular points of X, and that is the set of points at which X is n minus 1 dimensional CP manifold. And actually, the set of bit regular points of X is contained in the set of regular points of X at the definition of Guillaume-Vallet. And we take gamma X to be the complement of X regular P here, and call it the singular set of X. And for every X fixed, and we also consider a set VXX is a set of Y's in X regular P, so that the line through X and Y contained in the tangent as Y of the regular big regular points. So we consider sigma x and vxx as bad sets for x, and we take the union and we denote it by sxx, and we take all xx to be the complement of the bad set. So look at the picture. So x is like this. The set of singular point of x is the red one. And if x is here, so we have the set vxx is this line. And the union of this line and the singular set considered as the bad set for x. So we denote delta here is the set of x lambda t in order to n, so that x plus t lambda 1 contained in the bad set. And we also consider two map spin. The first one eta take x lambda t to x plus t lambda 1. And the second one is the projection for getting the t coordinate. And we take y to be the pre-image of x under the map eta, and y prime and delta prime are the image under the of y's and delta under the projection. So we have the follow property. So the dimension of the fiber of delta prime at x for every x in Rn is smaller than n minus 1. And if we fix x and we remove the Basque set, so the restriction function, the restriction map eta is a CP diffeomorphism. So actually, we have something called Basque set, but it's not a good set when we want to use cell decomposition. So we want to make another Basque set, which is a little bit bigger, which is allow us to work with cell decomposition. So we take D to be a CP definable cell decomposition of R2N compatible with Y and delta. And then this implies that D prime is the CP definable cell decomposition of R2N minus 1 compatible with Y prime and delta prime. And we take all the cell in D prime such that is a fiber at x for every x in Rn has dimension smaller than n minus 1. And we put them all together, we get a definable set and denoted by delta theta. And because of this property, so we have delta prime is contained in delta theta. So we have the result that if we fix x in Rn, so if the pole center at lambda star radius epsilon is outside the Basque set, then the intersection between x and the corresponding cone satisfies the property 2. So then we are ready to prove the main theorem. The first is we apply Nguyen theorem. We may assume that x had a good direction. So it means there's a neighborhood U of A0 such that the angle between lambda A with the tangent space as x of x for every x in the regular set of x is bounded away from 0. So it is known that the set of all lambda in Rn minus 1 such that by lambda restrict to x is finite is definable and then set in Rn minus 1. It means therefore it's contain a definable set which is open and dense in Rn minus 1. And we denote that open and dense set by Q, because U is open and Q is open and dense, the intersection have to be open and non-empty in Rn minus 1. And then we take B here to be a box in the intersection. And then we apply the lemma 4 to the data, including Rn, P, and delta theta. And we get a partition of Rn such that each element of the partition there is a box contained in P such that this intersection is empty. So it means the condition 2 is satisfied. So because we have the partition is finite, So in each box here, we can choose a vector inside. So because we have finite box, so we have finite vector. So we just check that lambda here satisfies the statement of the theorem. More precisely, the condition one is followed by B sigma containing Q, the set of all vector in Rn such that the restriction, the projection along this vector is finite. And the condition two follow from this condition and apply the lemma 2. And the third condition follow from the condition star from Nguyen theorem, saying that the angle between a regular good direction with the tangent space is bounded away from 0. So then we finish the proof of the main theorem. So here are the references, main references taken. And thank you very much for your attention.